Thank you for joining me today. I wanted to give you an example today of sketching a curve. So what we want to look at today is this function here. It is the function x divided by the square root of x squared plus 2. And we desire to get a graph for this, a nice pretty picture that uses not only algebra knowledge, but also the calculus knowledge that we have gained thus far. We don't need to forget the algebra though, so probably the first place that you should start when you're curve sketching is with the algebraic knowledge that you have gotten before this class. For instance, we could find the intercepts. So if I want to find the x-intercepts, what I'm going to do is set the function equal to 0. So I'm going to say f of x equals 0. Well, f of x here is this quotient. And a quotient equals 0 when the numerator equals 0 and the denominator does not. So this would imply that x would be 0. So I can draw the point 0, 0 on my graph. I do know that that will be a point when I actually sketch the entire graph. That will be one of the intercepts that I have. The way I find my y-intercepts, which is a little redundant here, but I'll show you anyway, is I allow x to be equal to 0. And if x is equal to 0, I get f of 0 is equal to 0 divided by the square root of 2, which is 0, which gives me the same point. Another thing that you might want to check for is symmetry. This is also an algebraic concept that you've probably seen before. The way I check for symmetry is I find f of minus x. And since the minus x is being squared, it reduces. And I can notice that this compares very easily to my first graph. It is actually the opposite of my first function. So this is minus f of x. When f of minus x equals minus f of x, I know that f is an odd function. An odd function has origin symmetry. So I know that what is in this quadrant will be reflected about the origin in this quadrant. What's in this quadrant will be reflected about the origin in this quadrant. If, instead of this, I were to get f of minus x equal to f of x, then f is an even function, which means it has y-axis symmetry. But here that does not happen. So let me recap. So far, we have found our intercepts, and we have discovered that this is an odd function. Both of these things are things that we knew how to do in algebra. Another thing that we probably need to talk about is the domain of the function. The domain of the function are all the values for which x makes sense to plug into the function. A lot of times a square root or a denominator will limit the domain of the function. Here it does not. The domain of the function is actually all real numbers, because what you're squaring here, x squared, is always bigger than or equal to 0, which tells me that x squared plus 2 is always bigger than or equal to 2. Therefore, I can't obtain a 0 in the denominator, nor can I obtain a negative value under the square root. Therefore, my domain is not limited at all. So that pretty much talks about a lot of what you discovered in algebra. There's a little bit of overlap from algebra and calculus when it comes to asymptotes. So with asymptotes, we could find vertical asymptotes by asking ourselves if the denominator equals 0 anywhere that the numerator does not. Those would give us vertical asymptotes. Here we do not have any of those. We could also find slant asymptotes when we have a rational function. Here we do not have slant asymptotes. We do, however, have horizontal asymptotes. And when we're trying to find our horizontal asymptotes, our question should be, what is the limit as x approaches infinity of our function? And then we should also ask about what is the limit as x approaches negative infinity of the function. So here, if I begin to calculate, I have to determine a way to talk about the limit of this as x goes to infinity. So what I'm going to do is divide the numerator and the denominator both by x. So I'm going to divide this numerator by x and the denominator by x. When I divide the numerator by x, I get a 1. When I divide the denominator by an x, let's go over here to look at this for a moment because it's a little bit more difficult. I want to divide this by x. Another way to look at this is x is the square root of x squared. So when I divide here, I will actually get the square root of 1 plus 2 over x squared. And now from our limit rules that we learned in Chapter 1, we know the limit of the numerator is a 1, and the limit of the denominator here, the limit of 1 is 1, and the limit of 2 over x squared as x approaches infinity is 0. So this is a 1. Therefore, I have a horizontal asymptote at, remember asymptotes are actually lines, so they're not located at a number, they're located at a line, and you need to write an equation for a line. This is at y equals 1. So I can put that horizontal asymptote in my graph. Let's go back and analyze the limit as x approaches negative infinity. So here, when I'm dividing by an x, and here, when I'm dividing by an x, do you see that this number is actually negative? So, as I go throughout this process, I have to ask myself, what will change? And if you discover as you're going, your limit will be at -1 rather than at 1. If you're worried about this concept, you can also ask yourself here, if you're plugging in negative numbers into this function, let's look right up here. If I'm plugging in negative numbers into this function, the numerator, we said before, was always bigger than or equal to 2, or the denominator is always bigger than or equal to 2. The numerator, however, will be negative. Therefore, when x is approaching negative infinity with large negative numbers, I will actually get a negative number in my function as well. So that gives me a horizontal asymptote at y equals -1. I know it's a lot of work, but we're almost halfway there. So let's look a little bit more at our calculus. So far, all we've done with calculus is taken limits. We also know how to differentiate. So let's start using our differentiable rules, and we might be able to find a little bit more information about our function. So if I find the first derivative, and I encourage you all to do this, I've done it ahead of time, so I'm just going to write it down. I get 2 divided by x squared plus 2 to the 3/2 power. And what I need to determine from this first derivative is where the first derivative changes sign from being positive to negative. Those are the places where I have critical numbers that could be my maxima and my minima of my graph. But if I notice what is happening here, remember the x squared plus 2, as we talked about before, is always bigger than or equal to 2. So if this is bigger than or equal to 2, and I take it to the 3/2 power, I still get something that is positive in the denominator, and I have a positive numerator. So this is always bigger than or equal to 0. It's actually strictly bigger than 0, or bigger than or equal to 0. So here, this tells me that I have an always increasing function. on the entire domain, my function is going to be increasing. If it were to change from positive to negative, then I would have to do a little bit more of a sign analysis and determine where it changes from increasing to decreasing. But since that doesn't happen here, I'm actually finished with the first derivative. I've gotten all the information that I need. The second derivative of the function, which I encourage you to find, but I have already found ahead of time, is a minus 6x divided by x squared plus 2, this time to the 5/2 power. If you will recall, once again, the x squared plus 2 is always bigger than or equal to 2. Therefore, when you raise it to the 5/2 power, you get a denominator that's always positive. I don't really care what it's bounded by. What I actually care about is the fact that the denominator is positive. Therefore, the second derivative is taking its sign directly from the numerator. So the second derivative changes sign where the numerator changes sign. So if I look at negative 6x, I see that if x is negative, the second derivative is positive. I have a negative 6x, so if I plug in a negative number, it's times a negative number, so it's positive. And if x is positive, the second derivative is negative. This tells me information about the shape of my function. Where the second derivative is positive, which happens from minus infinity to 0, the function is concave up. And where the second derivative is negative, which happens bigger than 0, or 0 to infinity, the function is concave down. So let's put this all together. We want to combine all the information that we have gleaned from analyzing the function, its derivative, and its second derivative. If I notice, I have an odd function, so whatever I draw here needs to be related to what's here as well. They need to be reflections about the origin. I need the function to always increase, which is why I'm talking about this quadrant and this quadrant, because I don't want to start here and end up down here. I want to start over here and end up higher so that my function's always increasing. I do also know that my function is concave upward from negative infinity to 0, and it is concave downward from 0 to infinity. And I have these horizontal asymptotes that my function should approach from one direction at least. So that yields a function that looks something like this. Thank you for joining me. Remember, if you're not having fun, you're not doing it right.